All right, let's talk gas stoichiometry. So here's the difference between our regular problems and gas stoichiometry. So when we look at number one, we have how many liters of our nitrogen gas at 115 kPa and 355 K can form from the decomposition of 35.8 sodium azide, whatever that is, NaN3. And the issue with this is that you might notice that NaN3 that it gives us in grams is a little bit different from the values that it gives us for the nitrogen gas, right? So if I were to kind of write this out, for my nitrogen gas, I have a pressure that is 115 kPa. I have my volume is what I'm trying to find, so that's my X. My N, I have to find, but it doesn't give me grams of nitrogen. It gives me grams of this sodium azide. So this is the only thing that's new, because now we've got to change that from the sodium azide into nitrogen gas. So that's where a little bit of the stoichiometry is going to come into play. So we'll come back to that. Let's just keep going with our PivNert here. Our R value that we're going to use, we look on our red sheet. We'll kind of come back to that as well. And then our T is already given to us in Kelvin at 355 K. So I think if we look on our red sheet, I'll pull this up in a second, I think our R value is 8.314. Okay, so right now we have two variables. We've got our N and also our V. But we could find N using a little bit of stoichiometry. So we look on our red sheet and we have our R values, again, that are organized based off of the different pressures. So that's why we chose our 8.314. And just to double check with on our red sheet that we're actually kind of, I guess, making sure we're checking all the boxes. Change grams to moles. We're going to work on that next. Milliliters to liters. We're trying to find the volume, right? So we'll come back to that one as well. We got to make sure our degrees are in, our degrees Celsius is in Kelvin. We already picked an R value and we're eventually going to solve. So the big key thing I want to point out on this slide though is this right here. Okay, so we've kind of been ignoring this up until this point. So our stoichiometry hints. So in this case, we are given a mass, right, or moles in the problem. So this kind of gives you a little indicator as to what you're going to do first and then what you're going to do second. So in this case, we're going to do the stoichiometry first, and then we'll plug it into the ideal gas law. All right, if we were given a volume, like you'll see in number 3 on that sheet, we would do the opposite. We'd do the ideal gas law, and then we would do the stoichiometry second. So let's go to plug this into our equation. So what we're going to do is we're going to do some stoichiometry. We've got our NaN3. We're trying to find N2. So I'm just going to start writing this out with a T-chart. So 35.8 grams of that NaN3. Okay, and if I want to change that to moles, so I'm trying to change it from one thing to the next, stoichiometry, so grams to moles. 1 mole of the NaN3 on top. And then we've got to go to the periodic table to figure out grams of NaN3. So we're going to look on the periodic table. We're going to find, here's our nitrogen. Over here is our sodium. So we've got, let's see here, Na is 23 plus 3 nitrogens. So gosh, 3 times 14, what is that? 42? 42? So that gives us 65 grams. All right, so we're going to take that, we're going to plug it back into our equation. 65 grams. Okay, so now I want to change that to nitrogen. So how do I change from one thing to the next? We're going to go ahead and look at the coefficients. So for every 2 NaN3, hopefully you remember this from the Stoich unit, we're going to have 3 moles of N2. And when we go through and we calculate that, now I can stop at moles because I don't need to go all the way to grams, right? I'm trying to find N of nitrogen. So I could stop at moles. I don't have to keep, when we did the stoichiometry, you went grams to moles, moles to moles, moles to grams. All right, but now we could stop here, and our calculation is 0.83, and again, that's moles of nitrogen, which is going to end up being our N. So from there, now we're going to plug that into Pivnert. PV equals nRT. So our pressure is going to be 115 times our volume. Our N is 0.83. We just found that. And the R value is 8.314. And our temperature is 355. And when I solve for V now, I'm going to divide both sides by 115 to get V by itself. What is our B? 21.3. The question is, what unit do we put on there? Because we need to have a unit. Remember, Pivnert is always in liters. Good. Okay. So why don't you go ahead and try number 2, and we'll go over that one. Okay, so very similar to number 1. When we look at this, we've got liters of hydrogen gas produced, 300K and 104 kPa, and it gives us a mass. It gives us the mass of sodium, and it says it's reacted with water. That's just extra information. We don't really need to worry about that because we're trying to find hydrogen, right? All of this stuff I highlighted in blue here, liters of hydrogen gas, 300K, 104 kPa. That all deals with hydrogen gas, H2. All right, but it throws in a mass of the sodium, which is Na. So again, looking at our red reference sheet here, we're given mass or moles of the problem, so we're going to do the stoichiometry first, ideal gas law second. For number 3, you're going to do the opposite. You're going to do the ideal gas law first, then the stoichiometry second. So I'm going to start off with my 20 grams of sodium. And what I'm going to do is I need to do a little stoichiometry here to find hydrogen. And I'm actually, if I plug this in, so it's important to know kind of what you're trying to find, right? So if I were to try and do Pivnert here, let me just try this out. So P is 104 kPa. My V is what I'm trying to find, how many liters. My N is also what I'm going to use stoichiometry to find, and then my R ends up being the same thing, 8.314, and then my temperature ends up being 300 Kelvin, right? So basically I'm trying to find this N. I basically have 2 variables, which can't happen. So point is that I can stop at moles of hydrogen because that's what N represents, moles. And all this information is based off of hydrogen gas, right? So all I have to do is convert this into moles of hydrogen. So for every 1 mole of Na, it's going to weigh 23 grams. And if I look at the coefficients in front of the numbers, so I can change this from Na into hydrogen, I'm going to put a 2 down here, 2 moles of Na, 1 mole of hydrogen on top. I get 0 0.435 moles of hydrogen, which is going to be my N. All right, so I'll be able to plug that in, and now I can just do the ideal gas law, pivnert, and plug these values in. So 104 times V equals 0.435 times 8.314 times 300. Divide both sides by 104. Or you can do the math, and then so you have 104 times V and then another number on the right hand side if you're worried about the order of operations. And we find that V, our volume, our end answer is 10.4. And now the unit, remember, we're dealing with the ideal gas law, so our unit has to be in liters. Hopefully this helps out. Definitely try number 3 because it's a little bit different type of a problem, and take a look at the next video if you need help with that.